I'm gonna walk around, so bear with me as I pull this out. Yeah, so on this talk, we've gone through a few applications in detail. So we've spoken through what are, want me to go up on the stage? Okay, Matt, I'll go up on the stage. Thank you. Yeah, we've spoken through a few in detail. We've introduced application models. We went to the one and opened it up and demonstrated how you can download it and use it. Several of the other applications there were also application models. So the CFB combustor is an application model, so you can download that and try it. The direct reduced iron application model is there, the bubble column. And if we did that for all the other applications, well, first of all, we don't have that many application models. And secondly, this would be a 2-day conference. So the goal here in this talk is to look at other applications, give an overview in different categories. For some of these, there are application models, so you on your own can go and see those and try them. And then other considerations. So we'll get to the end of this, and Shashank and I will alternate a few times where we have more experience in an area. And then we'll end with talking about, okay, there's applications we haven't even thought of here, or some of you have thought of, but they're not part of our slides. How would you evaluate what's a good fit for fluidization, for fluid particle simulation of Barracuda, and just talk about how to evaluate where Barracuda is suitable, and maybe think through where other tools are suitable as well. So with that, let's start with the first category. This is gasification, pyrolysis, plastics recycling. These are thermochemical conversion processes. And there's different types of gasifiers. Here's some from the literature of a moving bed and train flow, a fluidized bed, transport. And if we had this conversation 20 years ago, 25 years ago, we were speaking about coal or petcoke as the feed source. In fact, 100 years ago now, the Winkler gasifier came online, gasifying coal. And then what the trends we've seen is different feedstocks. So biomass is a little bit more complicated than coal in that there's some moisture to deal with. And this, by the way, is taken from, and again, all these slides will be made available from KW Tech. There's a reference here. This is taken from the presentation we did with Sungas Renewables a couple of years ago. And in their model, they had the biomass particle, and they assumed it was multi-component. So they had the water, this is moisture that can evaporate. There were volatiles that Shashank showed that go directly out into the gas phase. Char, which then reacts with the gases, and there's multiple gas phase reactions after that, and some ash that does not react. And we showed this early in the day, where we're looking at the gas composition and so forth. And so biomass gasification is a very common application for gasification or pyrolysis, very common application. But you can model other feedstocks as well. So municipal solid waste. Okay, this might look a little different. There may not be moisture in it, so you don't have that, or it could be, right? Maybe you do have to dry it, of course. But you still have the same mechanism. You may have a different composition of the particle. You may choose to use different kinetics and reactions, of course, that are more suitable for your feedstock. But it's the same sort of process where you have a multi-component particle coming out into what you're reacting. And same thing with plastics recycling. There's mechanical recycling of plastics is very limited. You need a very high purity product that's basically melted and extruded, and it loses quality every time. With advanced recycling, or sometimes called molecular recycling or chemical recycling of plastics, now you're taking the plastics, breaking it back down into the base molecules, and recreating plastic or other chemicals. It's the same sort of thing. It goes through a gasification or pyrolysis process. And we don't have an application model today for plastic recycling, but there's been a lot of work done by the customer base, and I think there's companies here that are working on this as well. There's a few things in the public domain. There was a great presentation by the University of Birmingham with some more innovative recycling technologies, which then rebranded. And Nelotech, and these are some public domain announcements. Aneltech and Cena spoke at a prior users conference on their plastic recycling application. We are a member of this consortium. And so Shashank, I said, why don't you speak a little bit? He's going to talk a little bit about modeling plastic waste.
All right, yeah, thanks, Peter. Again, this is, just going to briefly go over this. This is actually work that, again, was done in Korea. If this is papers from a few years ago, this is for waste plastic solid refuse fuel gasification. Work that was done by Korea Institute of Energy Research, Samkinkyang University of Seoul. Right. Again, thanks so much to the authors. They did use Barracuda for this work. So, okay. So I guess they are using what they call as, or what they have as a bubbling fluidized bed reactor here. As Peter was pointing out, the key idea is that if you're not familiar with solid refuse fuel, as I was not, a while ago, the key difference is that essentially when you have any non-recyclable high calorific combustibles from your municipal solid waste, essentially, right, that are not organic matter but they have high calorific value, you can convert them into solid refuse fuel. In this particular example, I think the others, there wasn't a lot of experimentation behind this, and they obtained flakes of solid refuse fuel from plastic, but that's what they're using. The key difference the authors point out between this SRF and biomass is that the high plastic content in SRF results in significant C1, C3 hydrocarbon molecules in the system. And then they also produce more tar than traditional biomass. So as I will show the kinetics on this on the second slide, there are many similarities even with any kind of gasification, whether it's coal gasification, and as Peter is pointing out, biomass gasification. And you still have those steps of, if there's moisture, there's drying happening, there's devolatilization happening, char-based reactions, gas reactions, everything. Those are all considered in this work, but because we're actually looking at plastics refuse fuel, the authors say that one must consider these C1, C3 hydrocarbon reactions as well. I'll show them in a second here. Again, they are using a bubbling fluidized bed reactor because of its high heat and mass transfer rates essentially. And what they've importantly done in this study is they've actually varied the equivalence ratios, and they've also varied where they're injecting the fuel, and they're looking at the yields of olefins and synfax, right? And syngas for this simulation. So without any delay, I'm just going to quickly show their domain. It's a very similar reactor that we have been looking at from a previous talk. Basically a cylindrical reactor, you have an air distributor plate through which you're injecting gas. Now this fuel inlet, currently it's shown to be injecting above the bed mass, but the authors have varied this location as they talk about in the paper. And then the outlet is towards the right of the reactor down here. The key thing is, the bed consists of silica bed material. Again, it is of a different PSD here. And the SRF particles are not spherical particles. In fact, the sphericity of the particles is close to 0.23. So they're like shredded, fluffy SRF particles of quite a different dimensions again. They are running this as isothermal. I've given the flow rates there. But if I point to the reactions again, they do say that SRF also undergoes drying, devolatilization, and heterogeneous char and homogeneous reactions, very similar to what we looked at coal. But in addition to that, they actually have these reactions for basically C1, C3 oxidation reactions. So you have these C1 to C3 sort of hydrocarbons, C2H2, CH4. All of these are reactions essentially, and they go from there are about 18 or 19 reactions just based for these in the paper. But the key idea is pyrolysis releases high yields of C1, C2 hydrocarbons and tars. And firstly, they account for the oxidation reactions. I'm only showing a few of them here. Similarly, they're also accounting for steam reforming reactions of the C1 to C3 hydrocarbons. Then the authors also account for certain tar decomposition reactions. Again, this is something that can be done in Barracuda. Many of our customers actually do this, right? And the authors are showing a great example of how they've implemented this within Barracuda. They have modeled these tars as phenol and naphthalene. again, because of the high plastic content in this SRF fuel. Okay, so I strongly encourage you to look through the paper. I've only captured a few reactions down here, but if you look at all the 1 to 16 reactions, are all these reactions, and beyond that are all additional reactions you would need for plastics gasification. All right, so very quickly, I've just got a couple of snapshots from their paper. They're showing the reactor here. You can see the sand, and you can see that the SRF particles settle down on the top. That's why all this are playing with the fuel location such that the SRF just doesn't move up the bed. But they also say that because of the lower density of these particles, they ideally want to then create those pellets by mixing some blend with high density fluid such that the mixing is good. But you can see this is a bubbling fluidized bed reactor with bubbles raising. And the key takeaway, right? Firstly, they are comparing some product yield gases with actually their experimental work down here. And the experimental work is the gasification, the light gray and the darkish gray simulation. You can see that they're comparing all the gases at the outlet, including all these C1 to C3. And they see a very good match between experiments and simulation for the most part. And then they did a couple of important results, right? I just wanted to point out, there are obviously many more details in the paper, but if you look at a couple of more results, firstly they say that when they reduce this equivalence ratio, that actually increases the yield of C1 and C2 there. So what they're saying is that a low ER autothermal gasification is actually a viable pathway for producing basic olefins for residual plastics. And the other important thing they're saying is that this feed location, as they change the feed location from above the bed into the bed, they're actually seeing a higher syngas composition. So again, there are many more details in the paper, and I encourage you to actually look at them.
Thank you, Shashank. And as we go through, you can see we're hitting on these topics much more quickly. We will have a discussion after this for questions and answers, so please, if we want to go in more detail, let's do it there. The next sort of category here is materials. And there's a lot of materials that are made in fluidized beds or fluidization process, fluid particle processes. We've looked at cement already, talked about a reduction of iron. A lot of well-established processes use fluidization. The very first user of the software that became Barracuda Virtual Reactor over 20 years ago was modeling a titanium chlorinator, polysilicon, ore roasting. And then there's these newer and emerging processes. Lithium, I'm sure a lot of people are interested in this. This is one of those areas where there's multiple applications for fluid particle processes. So the brine extraction itself can use a liquid particle process. And then as Reddy mentioned this morning, there are processes in the processing of the lithium to make battery materials, which I'm not seeing things in the literature, and with confidentiality agreements I can't talk about. But I do want to say, this is being used. It's in the public domain that it is being used for that. So if you are interested in or looking or using such a process, if there's a fluidized bed involved, please speak with Catering Tech and speak with us. I'll spend a little bit of time on carbon materials and other metals and materials. Nickels. We are right now involved in a nickel refinery that uses fluid particle process. And then rare earths, a lot of them in terms of slurry flows and others some of those could use fluidized processes. Touching on cement very briefly in just a couple slides. This is not really an emerging thing, but just to briefly mention, there's many gas particle processes in the cement process. So there's a lot of preheating that comes up to preheat the meal. These are typically done in cascading cyclones to preheat the material. There's a calciner. There's a kiln. There's a conditioning tower not shown. In the basic calcination process, cement is responsible for, depending where you look, 4 to 8% of global CO2. Now, part of that is it's a very highly endothermic process, is calcination. So you need to provide that heat. Historically, that has been done with a coal combustion. So reducing a lot of that with alternative fuels is of interest. But if you look at the reaction, guess what comes out? CO2. So you're not gonna get rid of all of it. But so there's a lot of interest here in that. It is a significant source. We do have 2 application models, and all I will do is say they're there on our website today. So if you're interested in cement calcination, there is one that can be downloaded today. And then the conditioning tower. This is that cooling the hot gas that comes out of the preheater cascade with liquid sprays. And so these are available today. Carbon materials. Carbon is a critical material for many energy storage applications. You know, a lot of this can come from, as Shashank mentioned, again, he's shown a lot of this, methane pyrolysis. We've talked about that from the perspective of hydrogen. So if you take a methane molecule, you split it, you can get two hydrogen molecules, 2 H2, and you're left with that carbon. What is that carbon? Is it carbon black? Can it be made into graphite? Can it be processed differently? And so all 3 of these materials, graphite, graphene, and carbon nanotubes, are or can be processed in fluidized beds or fluid particle systems. A few brief things, and there's links to it on our website. There's a company called Skeleton Technologies, and their news announcement, they talk about their supercapacitors being based on curved graphene as a customer of ours. We talked about this molten case in terms of the shaft furnace a lot. In fact, the original funding for phase 1 of that work came from, it was the U.S. Department of Energy funding that sponsored molten. They were working with U.S. Steel, and it was for hydrogen, you know, for decarbonization steelmaking. Well, I don't know if you ever follow international politics, but turns out the U.S. sometimes gets in the news, and there's a lot of views about our president one way or the other. But what I will say, I get at least a smile back there. What I will say is, good or bad, things change. And they change one way, and they'll change again. And all of a sudden, what we saw is that hydrogen was not highly funded. Well, guess what is? The byproduct is graphite. The domestic sources of graphite are highly important now. And wait a few more years and it'll change again. And it's a very robust process. So molten has actually had a lot of funding cut and is doing fantastic because in one sense they're making hydrogen and in another sense they're making graphite. And my point is not to poke fun of international politics so much. But fluidization is a very robust process and is used for a lot of things. So even if today we're not speaking on every application you have an interest in, please be aware that we're here to help, and this is a tool that can be very diverse. And then just decarbonization and carbon capture. I think Professor Lee, your talk covered a lot of this, but there's various ways this can be accomplished. So some of it is replacing fuels. We've seen this already in my talk, replacing fuels with lower carbon sources, so using alternative fuels in cement. In Shashank's talk, or POSCO, using hydrogen for iron, for steel making, ammonia co-firing. So some of this is replacing the fuels with lower carbon sources. Others could be avoiding or having concentrated CO2 streams, either avoiding them or concentrating them. So for oxy-firing, chemical looping combustion, I couldn't understand what you were saying, but I saw there were slides, so I trust this was handled very well. And then carbon capture reabsorbent. So the traditional amine process, of course, but the sorbent-enhanced steam reforming, these are sorbents in the bed that can be used to capture the carbon. And downstream, there's also processes that swing. So you take a CO2 and you adsorb it into the particle, and then you take that particle to another reactor, and the desorption happens. So this is chemical looping based on a presentation 10 years ago at a users conference. I do want to touch on an advanced nuclear as a topic. So there is something called trisofuels. So triso stands for tristructural isotropical particle fuel. And what it really is a central fuel core. This is typically a uranium oxide, there could be some carbon in there. And then it has multiple layers of carbon-based and ceramic-based containment. So typically there's the carbon buffer layer, and then various carbon-based. This is usually a silicon carbide, a ceramic, another carbon-based encapsulation. These are particles. So I won't go into the size, you'll see some of the literature, but they're, could be, well, they're very heavy. You can look at a periodic table and realize uranium is fairly heavy. But they're basically probably the LRB or probably more like D particle. And what's happening is these layers around the fuel becomes a self-contained pressure vessel that will contain withstanding temperatures that would be a runaway. This is the idea. Well, if this fuel, if this layer around the particle is the containment, then uniformity of application is critical. It's pretty important that that's on the right. Well, the way this is formed is chemical vapor deposition in a fluidized bed reactor. So we do have an application model. It's in development, so it's not ready today, but should be out here in the next month or two. And with the various deposition layers. And so the first, I took a screenshot here of the first deposition layer. This is formation of a carbon buffer layer around a central core of uranium oxide. You can see it's taking the gases. It's involving pyrolyzed acetylene in a spouted bed reactor, and it's taking and depositing carbon on the surface. Well, if we look at this in a simple geometry, and this is taken from the literature, this is a work in progress, but you see a spouted bed reactor, so pulsing with a high-speed upward flow and a slow downward flow along the walls. And here we see the particle size changing because of that chemical vapor deposition. And the critical thing is, are these uniform? Are there dead zones? And how does that work? So this is central to that coating process. All the stages, 3, 4, 5, whatever those stages are of coating. And in Barracuda, we're looking at not just visually, but in this case, these are fairly large experiments here of a particle, 1.5 millimeter, and looking over time as not just the size is shifting, but the particle size distribution is shifting. Is it fairly tight and uniform in moving over, or do you get bimodal distributions? And this would be a bad thing. So this is in development. It will be available soon. What we are finding is right now there's a huge surge in funding for TRISO fuels, advanced nuclear in the U.S., and I'm seeing that in different countries. We will have our first actual public presentation of this. This was our first speaker announcement for our users conference. Jared over at Kairos Power will be presenting on simulating TRISO coating in a fluidized bed CVD reactor using CPFD. So stay tuned for that. What we try to do with our users conference is record all the talks, post them to our website, and again, everyone is invited to join us in person if you're able. I realize it's a long flight. With that, I want to move to liquid-solid processes. So we developed liquid capabilities. I might just introduce this and hand it back to Shashank here. Liquid-solid processes, there's a lot of use cases. So some of what we're going to show here is an upstream oil and gas. While that might not be directly applicable, things like proppant flows is representative of slurry flows, where you have transport of slurry materials. So this could directly apply to pumping slurries maybe off the seafloor or other cases. And Shashank will talk about that. Sand screens. This is an example of recent features in Barracuda where there's a sand compaction around the wellbore, and you have particles that settle around this casing, but the fine particles are able to pass through a small buffer. The large ones do not. So this is some new capabilities. So in terms of example use cases, proppant flows, sand screens, completions, erosion of downhole equipment is very important, and this translates directly to many other applications. And hopefully during the Q&A we can hear from you on yours. Other slurry flows, and then liquid fluidized beds. We don't have anything to show on this right now, today, in the interest of time, but we do have ebullited bed reactors, slurry beds, and bubble columns are various applications that are enabled now. So with that, Shashank, I'll hand this back to you.
All right. Okay, so I guess I think this is a great point sort of to look into this, right, Elizabeth. I think we'll change gears a little bit. So far, we've showed you a lot of gas-solid flows with reactions and so on. Firstly, I don't know, with the raise of hands, I'm just curious to see how many of people down here knew that Barracuda could solve liquid solid flows like slurry flows. I'm just curious, with a show of hands, if anybody knew that you could use Barracuda to solve slurry flows other than just general CFD solvers. Not many people know that actually, but there are certain cases where Barracuda can actually be quite useful. Especially what we are finding is a lot of applications in this upstream oil and gas. So for those who may not be familiar, upstream oil and gas is the sector that deals with drilling of an oil well, the extraction of the oil from the well, right? So that whole process of drilling and extraction is what they call as upstream. Everything downstream is what many of us are familiar with here, refining of oil, all those, right? So the upstream side of things has very interesting multi-phase flow challenges around slurry flows. And so for that, I'm going to spend a little bit of time here going over this application here very quickly, right? Hydraulic fracturing, one way or the other, either good or bad, people might have heard about this. So hydraulic fracturing exists because there is a certain type of rock called shale rock, where oil doesn't freely flow through shale rock. The pores or the connections of the rock are not connected. Therefore, oil, just because you drill a well or a hole, oil is not going to flow into that and collect. So you will actually have to fracture that rock, break that rock such that you create oil pathways to extract the oil. That is what is known as hydraulic fracturing. So the way to do it is you pump from the surface. You bring in a truck which contains a slurry essentially with some sort of it's called slick water. So it's essentially some sort of a non-Newtonian fluid. You mix some polymer in the fluid to make it more non-Newtonian and viscous. And then you add a lot of solids. This could be as simple as sand, or it could be very advanced ceramic or hydrocarbon-based propellants. Propellants are nothing but solid particles, if you can think of them. So you are injecting this fluid and solid particles at a very, very high pressure. You inject it from the surface such that it comes straight into the pipe, and then this end is blocked, so the only way for that fluid to flow is through the rock. It just breaks open the rock, and that's how you produce oil, okay? So that's what this hydraulic fracturing is. Even if that is none of your concern, the key aspect here is that it is a slurry flow. The flow comes to the pipe, it has to enter these thin fractures. These fractures are what we will show you where you can actually model some slurry flow going into that. Okay. All right, so again, just like many other examples, it's virtually impossible, especially in upstream oil and gas. They have very little data on what is actually happening inside, because this well hole can be several hundreds of feet below the earth. So usually information that you obtain is not abundant, and it's almost impossible to visualize something like this. So therefore, a lot of modeling is what is needed to understand this. So let's look at a realistic example, right? I'm going to show you very quickly an example where, I showed you just these fractures, right? I'm going to show you 3 of these fractures, 1, 2, 3, and I'm going to vary the spacing between these fractures, and I'll show you how the slurry flow distribution will vary between the first, the second, and the third fracture as the distance between them varies. Right? That's all. So if I can skip through, let me show an example down here. So imagine this is a fracture that I was showing you, right? This is a slightly idealized version. It's a thin. This is only about this is like a 0.6 inch beginning to 0.4 inch thickness. That's how thin this fracture is. And I've got 3 of these fractures. This is that pipe I was showing, the horizontal pipe or the slurry. So the slurry comes through here, and this end is blocked. So the only way for the slurry is to exit through these fractures. What I'm doing is I'm varying the spacing between those fractures, 5 meters, 10 meters, 20 meters. And if you look at the domain sizes here, right, I have some of these fractures lengths are hundreds of meters here. You have 60, 50 meter long, and in feet it's close to 200 feet. And then they're also extremely thin. They start off at 1 inch and they taper off. The width of the thickness is 1 inch here, it becomes 0.6 inches and so on. So very, very unique geometries, right? Geometries of this size that you may not be quite familiar, but something like that can also be modeled within Barracuda. All right, so let me show you two pumping flow rates. They measure in barrels, unfortunately, in oil and gas, so that's what the unit I'm using is barrels. So you have 30 barrels per minute and 45 barrels per minute. As I said, the end of that well is closed, so the only way for the proppant is to go to the fracture. I am using a full PSD. Again, it doesn't have to be gas solid. Even for liquid solid, I have to use the full proppant because the settlement behavior of the proppant due to gravity, as it loses momentum, is based on the size distribution, just like you will have inside your gasifier, right? So again, capturing PSD, even in such a diverse application like proppant transport, is quite important, and that's where the strength of a tool like Barracuda comes in. All right, so, and lastly, right, this actually is amazing if you look at it. We are modeling that 200 feet long fractures, and we are simulating for 20 minutes of pumping flow from the top to the bottom into those fractures. And we are doing that in an average of 17 hours. We are running these simulations around, and we are simulating about 20 minutes worth of simulation time. So again, the GPU acceleration of Barracuda is where the strength is. Some of our users who have used traditional CFD tools, in fact, they came to us with this problem because while their traditional CFD tool was solving the problem, it was taking them about 5 weeks to get it out, even with 2 fluid models. And Daejeon was almost impossible to solve at this scale. So this is where, again, the strength of MPPIC technology lies. All right, I'll just quickly walk through the slides here. This is 40 by 70, different spacing, 5, 10, 20 meters. What you're seeing is slurry is coming from the left, and it is going through the fractures. It is leaving the fractures. Now what you'll see is, when it's only 5 meter spacing, slurry is able to make into the third fracture as well, a little bit. Not much, but a little bit. Why do I want my slurry to go into each fracture? Because if the slurry doesn't go into that fracture and the solids don't settle down, once I stop pumping, that fracture will close because there is tremendous amount of pressure of earth, right? So I want my solids to settle down along the length of the fracture to keep it open. 5 meters, I can get some, but 20 meters, none of the slurry goes into the third fracture. Why is it? Basically, the frictional losses dominate, essentially, and the solids are not able to make it to that. The physics, there are no reactions in there. It's probably not as complex as some of the fluidized reactors you're working with. But nevertheless, this is quite important physics, to look at, because this is not, we are not looking at single phase flow distributing like among like a T-junction. This is slurry flow with solids in there. So you have to account for both frictional losses of the fluid as well as the effect of the solids on the wall, along with the interaction that happens between the solid and the liquid with non-Newtonian drag. Okay, so then, okay, fair enough. Last fracture doesn't get. What if I increase my flow rate? I go to 45 barrels per minute. Okay, so this is just a measurement of total mass. So the same 30 meters per spacing I was showing, or so 30 barrels per minute. I'm showing you that how much total mass of proppant or percentage of mass enters each fracture. So you can see that 5 meters, 10 meters, 20 meters, as I increase the spacing, basically more, end up having more mass going into the first fracture and little in the third fracture, right? Again, as I said, pipe friction makes it harder to travel. All right, what if I increase the flow rate, 45 barrels per minute? 45 barrels per minute, and I'm just looking at this 10 meter spacing. Yes, now I see that increased flow rate. I definitely see more proppant settling down in my third fracture compared to this case. If I just numerically compare it, I do observe that numerically as well. If I measure total amount of mass. Again, the results are self-explanatory, so I'm not going to spend a lot of time on it. But again, the key takeaway is, okay, you might come back and say to me, we don't model oil and gas, we don't do proppant transport down here. But I was doing some research recently, and many of you might be familiar here. The Korean government is investing a lot into rare earth metals extraction. In fact, there is a mandate by 2030 actually to secure some of those supply chains. And these rare earth metals are found under the bed of a sea, essentially. So you have to do deep sea mining to extract some of this material. Imagine how of all of this slurry material is going to come from the bed to the ship. It is slurry flow through a vertical pipeline or inclined pipelines. So while here the flow is going from top to bottom, there the flow is going from bottom to the top. So Barracuda can be a great software to solve problems like this. I just want you to keep this in mind if you are going to start looking into applications like that.
Thank you, Sean. And that's the point. We cannot talk about every possible application you have. And please, during the question and answer, let's have a discussion. But we want to give you tools to evaluate, is Barracuda a fit for some of these? Some questions to ask. In general, are both particles and fluids, whether it's a liquid or a gas, are they important to your system? Are discrete particle properties important? And then not necessary, but is heat transfer and chemical reactions, are you trying to take it further? And this is usually a good fit for Barracuda. And then the scale. There's a lot of methods, very, very detailed methods that work on smaller scale but are difficult to extrapolate to full scale. With the last few minutes here, I want to talk about granular flow modeling, and there's a lot of CFD. I get asked a lot about, how we compete with CFD DEM. So for the modelers in here, how does this compare? And I will say actually there's broader applications, not just CFD DEM. There's the two-fluid model is probably the first approach for modeling multi-phase systems. It doesn't capture natively particle size distribution, so I'm not going to talk about that here, but there's great researchers who've done some work with that. But commonly we come up against the CFD DEM. And the point I want to make is how we complement each other rather than compete with it. So on this axis here, the horizontal axis, on the left I have pure particle systems, so granular systems. So fluid doesn't matter, it's pretty much just particle flow. Picture rocks avalanching downhill. On the other scale I have fluid flow only, there's no particles. So for cases of granular flow, DEM, who's familiar with DEM? Does anybody know what I'm talking about when I say DEM? Okay, I'll take a moment. Discrete element method is basically calculating just particle flows with Lagrangian particles. So it does a great job for dry granular. CFD, computational fluid dynamics, typically does a great job. It was built for fluid flow. But as you come in between, whether it's high density particle fluid flow or low density, you have this range where both the fluid and the particle matters. And there's a couple different approaches for that. One is CFD-DEM coupling. That is basically solving computational fluid dynamics and then coupling with DEM. DEM looks at where every particle touches every other particle. This is why it does detailed collisions. So how do they bounce? What Barracuda does is it takes that and puts it through models. So on a statistical basis, on average, what would happen if particles collide, which is typically more scalable. And so I want to talk about this. So for DEM, for dry granular DEM, for pure fluid flow, CFD is typically a good fit. And then in this range, you have two different tools which tend to work, but they tend to live in different spaces. So if these smaller scale, local effects, local details around a jet are important. CFD-DEM coupling typically does well on that, can do well on that. If the primary interest is a large scale system, you've seen some very large scale systems with very long transients, that's where the MPPSC approach, what Barracuda Virtual Reactor is based on, is typically dominant. But you can look at this in others. You can look at particle counts. So if it's a small particle count system, typically CFD small is relative. Please keep this in mind. Typically that's where CFD-DEM, sometimes with a coarse graining approach works. As you go to very large particle counts, that's where Barracuda Virtual Reactor has a very distinct advantage. What's the dominant physics? Is it direct particle contacts that matter most? Or is it fluid particle drag that dominates? As you go to, this is a fluidization workshop, so as you go to drag dominated systems, again, this is where Barracuda Virtual Reactor tends to have an advantage. Particle-particle interactions. If you're looking at shape effects where individual particle collisions, how they interact and interpack matter, that's a really good fit for CFD-DEM. Barracuda can handle these, But keep in mind, they come in through models. So if you have different shaped particles, you may have a different drag model. If you have different surface area, you may have different reaction rates or heat transfer coefficients. So it's still captured, but through the models. And then really, are you adding extra? So if it's just the hydrodynamics, that's CFD-DM typically can do that to a certain scale. Moving to include heat transfer and chemical reactions, this is something Barracuda is particularly good at. And then there's other things, moving geometry. If I gave this slide, and this actually came from a joint talk I gave with Altair, now acquired by Siemens, a few years ago. If it was primarily moving geometry, that was for CFD-DM. We didn't have any moving geometry. Now we have some, but it's still fewer capabilities. So just some tools and frameworks, as you've heard a lot from us, but there's a lot of other methods out there. We want to give you a framework to think through this. And really, if you have any questions, talk to us. Talk to Cato Tech, talk to us here. So that's the end of this particular presentation. I think I've gone over, so are we holding all the questions till the end? Or should we have time for a question? Maybe one?
Yes.
There's a microphone. Oh. Is there a microphone coming? Yeah, there's a microphone. Just a moment, sorry.
Yes, thank you for your sharing. Because you just mentioned about the transfer fuel that is in the future plan for the CPU software, and I saw you show the particle size change, right? So I have a very simple question: is that is this have some case that when particle size change like that, and is gonna change the gross breaking limit of this particle species? So is it possible to take into account that in the next release?
Yes. So, well, sort of. Let me think through this, and Shashank, you correct me if I'm wrong. Right now, you can have a closed pack limit, and that closed pack limit is the same for traditionally for all particles. So as you has a size distribution, you can still have one closed pack limit. Today, you can actually have different closed pack limits for different particles. So if you have multiple species, it is possible to have a finer closed pack limit for one than for the other, or a higher one. And then as you have a mixture, it'll look at what particles are in the cell. So cell by cell, you can have a different one. In this case, with chemical vapor deposition, it's the same species that's growing. So I think right now, there's no way to do that. Is that correct?
Yeah, that's right. Yeah. Right now, no, that is not something, but that is something we are considering. Is basically
Is this technical challenge, or is
that's
it
right.
possible
Yeah.
technically, right?
Yeah, so no, it's not up for the next release, no. But I think that is something that has come up a few times where we do want to have, basically, as you call it, local closed pack volume fractions, right? Depending on if there's local PSD that's different, that can change. Yes, that is something under consideration for development here. But as of now, if it is the same species, it will have a constant, what I call a single closed pack volume fraction. Different species, though, can have different closed pack volume fractions.
Thank you.
You thought a lot of application. So if I use the application, is there no function issues?
Oh yeah, we do want you to use those applications. All the application models that we have written are all from published papers. So those are not proprietary. Whether there is a geometry, that geometry has already been published in that paper. They have given us dimensions in the order. They have published those reactions, right? There is nothing proprietary in that application models that you cannot use. So that's the whole idea for them, is that you are able to download them and use them. Yeah.
Verification is
It will- Verification?
Yeah.
Yes, you can do that. Yeah, so fair enough. I think that was my question, is when can users submit their application models? The question then is, obviously that is a welcome move, But there is some this thing about where you have to look at the model, the implementation, how it is working out, and so on. These models we try as much as possible to, if there's validation possible, we do that. But again, the main objective is not to sort of it's not an academic thesis per se, right? We are trying to provide the user collect all information in one place and provide to the user, so you have a starting point. If that is just a starting point for you, you want to build on it, you don't have to start from scratch. You already have something to do.
And just maybe two thoughts on that. One is if you do use an application model and take it further and publish on it, we just ask that just like you would reference a paper, reference where this came from. And then a word of caution. We have taken things from the literature and we have shown how you would model it in Barracuda. That does not necessarily mean it's appropriate for your system. So this was kind of our hesitancy in doing it years ago, because what if we're endorsing, what if the Barracuda kinetics for gasification aren't good? Well, they were for this case, but maybe they're not applicable to your system. So please, it's a room full of engineers, please keep your engineering hat on and evaluate everything you're doing to make sure it makes sense.
Just to add to Peter's point, as you know with publication, there are many typos, many errors, you find them sometimes missing information. So we do our best to understand if there are any issue, mistakes, errors, and so on. But it's always possible that there's something has missed. It's what's being published is what we're doing. There's something there. We try our best to catch it. But again, all the references are given for the papers. So please look through those papers as well, so you get an understanding of what's happening.
My name is Namsoo Kim from Korea Institute of Energy Research. Thank you for your presentation. I have two questions. And my first question is, when we move to the renewable energies like plastic or waste, something that we have to use more larger chemistry mechanism, which could have 100 species and 1,000 reactions. And I want to know how your program can deal with this complex chemistry problem. And second one is, what is the main difference between gas-solid fluid system and liquid solid fluid system in Millennium perspective?
Okay, maybe I'll answer the first,
Yeah,
you know,
sure,
just a
yeah.
second. So in terms of the number of reactions, my answer to this question has changed over the years. So if you go 10 years ago, I would say, look, we're not doing a complex reaction mechanism, maybe 5, maybe 10 reactions. If you go back about 5 years ago now, we've parallelized all the major functions on GPU, including chemical reactions, and we saw a massive speed up then. And at that time, I would tell people, in fact, we've had people test and go up to say 20 or 30 reactions. It's still not 1,000, but 20 or 30 reactions. Since then, there's a couple things that have happened with efficiency gains, GPUs themselves getting faster, but also multi-GPU computing, and just overall numeric improvements. And we have actually just made an announcement last week for a speaker at our users conference. It'll be the Argos group will be co-presenting with my colleague Sam Clark, and they will show actually it's a partial oxidation unit downstream of gasifier for tar cracking, and they took reactions from GRI Mach 3 and put it in there, and that one has over 200 reactions solved together with the hydrodynamics and thermal in Barracuda. When I heard that number, I didn't believe it, and then I confirmed with my colleagues. So now something like that is possible. So you're still not doing 1,000, but it's a lot more than I've ever seen. Yeah.
How many reactions can be good for this situation?
Well, in this case, practically it was 200. They were okay with it. We still try to do something that's 30, 50.
That's right, yeah. So again, I've worked a little bit with GRI. So theoretically, yes, you can add more and more, right? But at the end of the day, if you have 1,000 reactions, that simulation will be more slower than 200 reactions. That's just a given. Again, if all those 1,000 reactions are happening simultaneously, let me correct this way, then yes, you will, even whether 200 reaction is faster, 1000 reaction, obviously the 200 will be faster than 1000, right? So that's something to keep in mind. Again, with CFD, we are not just purely solving for chemistry, right? We also have flow. So the user always has to think about what reactions are important. Can I get away using a 200-step process, or should I use a 1000-step process? Right? Again, so that judgment is still on the user. But again, there are very few CFD solvers which can handle 200 reactions. That too stably, right? That's the key point here. Running a simulation stably with 200 reactions is extremely, it's a very stiff problem. And to answer your question about liquid solid and gas solid flows, per se in the architecture of the flow itself, of the solver itself, the way it's built, right? It's pretty much the same for us, whether the fluid, again, I'm just talking about cold flow, whether it's cold flow with gas. Obviously gas is it's a compressible flow solver. You have to account for the compressibility that is going on. Here it is an incompressible flow solver on the liquid solid side. So what happens is with the incompressible solvers, on the solver side, in fact, depending on the application, you might be actually able to do the simulations run much faster, right? Depending on, there's not a lot of density changes with temperature and so on going. Usually incompressible flow solver run even faster for you. So other than that, it's the same GPU acceleration behind it and all of that. That is also remains very similar.
I would add that for liquid systems, you typically have longer, just in our experience, longer characteristic time scales, so they run faster, but you also may have to
Run them longer, yeah.
And then in some cases, if you have bubbles, there may be forces that are irrelevant, but like a virtual lift force or something that those are accounted for.
So, yeah.
I think in terms of timing, there is a whole Q&A session. Perhaps we should do the final talk.
Okay.
The die and reduced order model, if that's okay, and then we can open it up for all the questions. So, with that, we're going to transition over to Shashank's final talk.
Okay, that's it.
네, 그럼 오늘 발표